groceries are also likely to buy wine.
I see, it adds a numerical dimension to the rules, making them more precise.
Right. And they discuss various techniques for handling these continuous attributes, like discretization.
Discretization.
It means dividing the range of values into categories. So instead of using age as a number, you might have categories like young, middle-aged, and senior.
Makes sense. So you basically transform those continuous attributes into categorical ones.
Precisely. Then they introduce the concept of concept hierarchies.
Concept hierarchies.
Think of it as organizing items into a hierarchy. Like in a supermarket, milk and cheese might belong to the category dairy products.
I see. So instead of just rules about individual items, we can have rules about broader concepts.
Exactly. It allows for more general and meaningful patterns to be discovered.
That's cool. What else is there?
Well, they delve into sequential pattern mining. This takes into account the order of events.
Oh, so instead of just co-occurrence, we're looking at the sequence of actions.
Yes. For example, a customer might buy a smartphone, then a case, then a screen protector. That's valuable information for retailers.
It is. It allows them to predict future purchases and recommend relevant products at the right time.
Precisely. And they discuss specialized algorithms for discovering these patterns, like the GSP algorithm.
So it's like uncovering the narrative hidden within the data, seeing how events unfold.
A great way to put it. But sequential data can be messy. There might be gaps, noise, irregular time intervals.
So cleaning and pre-processing that data is crucial.
It is. And choosing the right parameters for the mining process is important too.
To ensure we're finding meaningful patterns and not just random noise.
Exactly. And finally, they introduce subgraph pattern mining, which is probably the most complex concept in this chapter.
Subgraph pattern mining. Tell me more.
It takes association analysis to the world of graphs. Nodes represent entities, and edges represent relationships.
So, like in a social network, nodes would be people, and edges would be friendships.
Precisely. And we can use this technique to find patterns in complex networks.
Like identifying groups of friends based on their connections.
Yes. They mention an algorithm called G-span, which is specifically designed for this task.
It sounds computationally challenging to find those patterns in large networks.
It can be,
Huh.
especially when dealing with graph isomorphism, which means determining if two subgraphs are structurally the same.
Right. And the number of possible subgraphs can explode as the network grows.
Absolutely. So efficient algorithms are crucial for subgraph pattern mining.
It seems like association analysis gets really complex when we go beyond simple item sets.
It does, but it also becomes much more powerful and insightful.
Well, let's move on to Chapter 8, where we return to cluster analysis.
Back to clustering. What new adventures await us there?
This time we're going deeper into the practical issues and considerations involved in applying clustering algorithms to real-world data sets.
So it's like we've learned the basics, and now we're getting our hands dirty with real data.
Exactly. The book emphasizes the importance of understanding the characteristics of our data before applying clustering algorithms.
Like dimensionality, sparsity, noise, outliers. All these factors can influence the outcome of a cluster analysis.
Right. It's like trying to find patterns in a messy room. If we don't tidy up first, we might miss important details or get distracted by clutter.
A great analogy. Data preprocessing and cleaning are essential for successful cluster analysis. And then, of course, we need to choose the right clustering algorithm for the job.
The book delves into specific issues related to different types of clustering algorithms, starting with prototype-based clustering.
Prototype-based methods like k-means and k-medoids are popular choices.
Right, they represent clusters by prototypes, such as centroids or medoids.
Exactly. K-means uses the mean of the data points as the prototype, while k-medoids uses the most central data point.
They both aim to create compact, well-separated clusters. But, like all algorithms, they have their limitations.
One challenge is dealing with outliers, those data points far from the others. Outliers can skew the cluster prototypes, leading to inaccurate groupings.
And the initial choice of prototypes can also impact the results, right?
It can. Different starting points can lead to different final cluster structures. So robustness and careful evaluation are essential.
It's like trying to organize a group of people into teams based on their interests. If we start with the wrong grouping, we might end up with unbalanced or unhappy teams.
Exactly. Then they introduce fuzzy clustering as an alternative to hard clustering.
Fuzzy clustering. That sounds interesting. What's the difference?
Well, in hard clustering, each object belongs to one and only one cluster. But in fuzzy clustering, objects can have partial membership in multiple clusters.
Oh, so it's like saying someone can be a little bit of this and a little bit of that instead of forcing them into one category.
Precisely. It's a more flexible approach that acknowledges the ambiguity often present in real-world data.
They discuss fuzzy C-means, which extends K-means by assigning membership weights based on distance to cluster prototypes.
Right, so the closer an object is to a prototype, the higher its membership weight in that cluster. It's like a gravitational pull towards the cluster center.
And there's a fuzziness parameter that controls the degree of overlap between clusters.
Exactly. Higher fuzziness means more overlap, fuzzier boundaries. Lower fuzziness means more distinct, well-separated clusters.
It's like adjusting the sharpness of a photo, making the edges more or less defined.
I like that analogy. Next, we delve into model-based clustering, a more statistically rigorous approach.
Model-based clustering sounds pretty fancy. What's the idea behind it?
It assumes that the data is generated from a mixture of probability distributions, each representing a cluster.
So it's like saying each cluster has its own unique statistical fingerprint.
Exactly. And the goal is to find the best fitting probability distributions for the data, estimating the parameters that define each cluster.
They focus on Gaussian mixture models, which assume the data is generated from a mixture of Gaussian distributions.
Right. Imagine each cluster as a cloud of points with its own center, mean, and spread, covariance.
And the algorithm tries to find the best fitting Gaussian clouds for the data.
Precisely. And they discuss the expectation maximization algorithm, a powerful technique for estimating the parameters of those Gaussian mixtures and assigning objects to clusters.
It's like a dance between the model and the data, with each step refining the other until they reach a harmonious agreement.
A beautiful way to describe it. Then they move on to density-based clustering, which focuses on the density of data points in the feature space.
So instead of distances to prototypes or statistical models, we're looking at how tightly packed the points are in certain regions.
Exactly. Density-based methods like dbScan and dinclu are particularly good at handling clusters of arbitrary shapes and varying densities.
Right? Unlike k-means, which tends to favor spherical clusters.
They explain how dbScan defines clusters based on core points, border points, and noise points.
Core points are those surrounded by many neighbors, while noise points are the loners, right?
Exactly. And they emphasize the importance of choosing the right parameters for dbScan, especially epsilon, which determines the radius of the neighborhood used to define density.
It's like adjusting the zoom level on a map. Too zoomed in, and we might miss the big picture. Too zoomed out, and we might lose important details.
A good analogy. Then they introduce dnslu, which uses kernel density estimation to create a smoother, more continuous representation of density.
So instead of dividing the data space into discrete cells, dnslu creates a smooth density landscape.
Right. It's like painting a landscape with watercolors instead of using a mosaic. It provides a more nuanced picture of the data's density distribution.
I like that analogy. And the choice of kernel function and bandwidth influences the smoothness of the density estimate.
Exactly. It's like choosing the right brushstrokes for our painting. Then we shift gears to grid-based clustering, a technique that partitions the data space into a grid and performs clustering on the grid cells rather than individual data points.
That sounds like a good way to handle large data sets.
It is. By clustering cells instead of individual points, we significantly reduce the computational burden.
It's like analyzing a map by dividing it into regions and studying each region's characteristics rather than examining every single location on the map.
A great analogy. They explain how different grid-based clustering algorithms use various strategies to group cells into clusters. Some focus on density, others on distance.
And like with any technique, there are advantages and limitations to consider.
Right. Grid-based clustering is scalable and efficient, but the choice of grid resolution can affect the results. Too coarse, and we might lose detail. Too fine, and we might overcomplicate things.
It's about finding the right balance between efficiency and accuracy.
Exactly. And finally, they discuss graph-based clustering, a technique that uses the structure of a similarity graph to group objects into clusters.
So instead of just looking at the features of the objects themselves, we're considering the relationships between them.
Precisely. Imagine a network of interconnected dots, where each dot represents an object, and the lines between them represent similarities or connections.
Like a social network, where people are the dots and friendships are the lines.
Exactly. Graph-based clustering analyzes these connections to identify groups of closely related objects.
They introduce different graph-based clustering algorithms, each with its strengths and weaknesses.
Some, like minimum spanning tree clustering, focus on finding the shortest paths between objects, while others, like spectral clustering, use more complex mathematical techniques.
And the choice of similarity measure is crucial for constructing the graph.
Absolutely. It determines how we quantify the relationships between objects, which can significantly impact the clustering results.
It's like choosing the right type of map for our journey. A road map won't be useful for driving, but a topographical map might be better for hiking.
A perfect analogy. Well, that concludes our exploration of cluster analysis, a fascinating world of techniques for grouping objects based on their similarities.
It's been a great journey through the clustering landscape, learning about the diverse ways we can uncover hidden structures in data.
It has. Now, are you ready to tackle a new challenge?
Always. What's next on our data mining adventure?
Anomaly detection. It's about finding those rare and unusual instances that deviate from the norm, those outliers that stand out from the crowd.
Like finding a needle in a haystack, or maybe a rogue data point hiding in a sea of normal data.
Exactly. And the book emphasizes just how important anomaly detection is in various fields.
Oh, I can imagine. Fraud detection, intrusion detection, medical diagnosis, anywhere where spotting those unusual events is crucial.
You got it. Catching a fraudulent transaction or a security breach early on can make a huge difference.
Absolutely. It's like noticing a tiny crack in a bridge before it becomes a major problem.
Perfect analogy. And the book dives into the key properties of these anomalies.
Like what makes them stand out? What makes them anomalous?
Well, for one, they're rare. They don't occur very often compared to normal instances. And they're distinctive, meaning they have unusual characteristics that set them apart.
So it's not just about being different, it's about being different in a way that's significant.
Exactly. And of course, the impact of an anomaly depends on the context. A misdiagnosed medical condition has a much different impact than, say, a slightly off-sensor reading in a manufacturing plant.
Makes sense. So how do we go about actually detecting these anomalies?
The book categorizes anomaly detection methods based on a few factors.
Like what?
Well, do we have labeled data, meaning do we already know which instances are normal and which are anomalies?
So that determines whether we can use supervised learning methods.
Precisely. If we have labeled data, we can train a model to distinguish between normal and anomalous instances.
But what if we don't have those labels?
Then we can use unsupervised methods, which rely on the inherent structure of the data to identify outliers.
So it's like having different detective tools depending on the amount of information we have to start with.
Exactly. And there are also semi-supervised methods, which use a small amount of labeled data to guide the process.
Okay, so a mix of both worlds. The book then gets into specific anomaly detection techniques, starting with statistical approaches.
Statistical methods often assume that the normal data follows a known distribution, like a Gaussian distribution.
So anything that deviates significantly from that distribution is flagged as a potential anomaly.
Exactly. They discuss techniques like Grubb's test and Dixon's Q-test, which can help identify outliers in a data set.
Those sound familiar. They're statistical tests for univariate data, right?
They are. And they also explain how to calculate z-scores.
Z-scores measure how many standard deviations a data point is from the mean, right?
Right. So a high z-score, whether positive or negative, indicates that a data point is far from the expected center of the distribution. It's a way to standardize the measure of unusualness.
Like a statistical red flag.
Exactly. Then they dive into proximity-based approaches, which utilize the distance or similarity between data points.
So if a data point is far away from its neighbors, it's more likely to be an anomaly.
Precisely. They introduce the k-nearest neighbor distance as a simple measure of anomaly.
Where we look at the distance to the kth nearest neighbor. So if a point has very few neighbors within a certain radius, it stands out.
Right. And then there's local outlier factor, or LOF, which takes into account the relative density of a data point compared to its neighbors.
So if a point is in a much sparser region than its neighbors, it's flagged as an anomaly.
Exactly. It's like comparing the population density of different city blocks. A block with significantly fewer people than the surrounding blocks might be an indication of something unusual.
I see. Then they explore clustering-based anomaly detection, where clustering algorithms are used to identify outliers.
The idea here is that anomalies often don't belong to any well-defined cluster Or they might form their own tiny, isolated clusters.
They're like the pieces of a puzzle that don't quite fit anywhere.
A great analogy. And the book emphasizes that different clustering algorithms have different strengths and weaknesses for anomaly detection.
So choosing the right algorithm for this specific data set and task is important,
Oh, it is. They also introduce one-class support vector machines, or OCSVM.
which are specifically designed for anomaly detection, right?
Exactly. They learn a boundary that encloses the majority of the data points, and anything outside that boundary is considered an anomaly.
So it's like drawing a fence around a group of sheep, with the outliers being the sheep that wander off on their own.
And as with traditional SVMs, the choice of kernel function can impact the performance of OCSVMs.
Right. The kernel trick allows us to handle non-linearly separable data. And, of course, evaluating anomaly detection methods can be challenging, especially when anomalies are rare.
Exactly. Traditional metrics like accuracy can be misleading in those cases.
Because a classifier could just predict normal for every instance and get high accuracy, even if it misses all the anomalies.
Precisely. That's why metrics like precision, recall, and F1 score are more suitable for evaluating anomaly detection systems.
They provide a more balanced view, considering both the correctly identified anomalies and the false alarms.
And they also discuss ROC curves and precision recall curves as visual tools for evaluating these systems.
Those curves can help us see how the performance changes across different thresholds, so we can choose the threshold that works best for our specific needs.
Exactly. Now, are you ready for the final chapter?
Bring it on. What's the grand finale?
Chapter 10 focuses on avoiding false discoveries, a crucial topic for any data analyst.
It is. We can't just get excited about finding patterns without making sure they're actually meaningful.
Right. We need to be careful not to be fooled by random fluctuations or spurious correlations.
So this chapter is all about statistical rigor and a healthy dose of skepticism.
Exactly. They lay the groundwork for statistical testing, introducing concepts like hypothesis testing, p-values, significance levels, and effect sizes.
It's like setting up a courtroom where our findings are put on trial.
And the p-value is the evidence presented against the null hypothesis, which assumes there's no real effect.
And if the p-value is low enough, we reject the null hypothesis and conclude that our findings are statistically significant.
But they also emphasize that statistical significance isn't the whole story. We need to consider the effect size as well.
Because a statistically significant finding might not be practically meaningful if the effect size is very small.
Exactly. Then they delve into the challenge of multiple hypothesis testing.
Ah, yes. When we perform many tests, the chances of finding at least one statistically significant result by pure chance increase.
It's like flipping a coin many times. You're bound to get a few heads in a row, even though the probability of getting heads on a single flip is 50%.
So we need to adjust our expectations and use appropriate corrections to avoid being misled by those random occurrences.
They introduce techniques like the Bonferroni correction, which adjusts the significance level to account for the number of tests performed.
Making it harder to claim a finding is significant when we're doing many tests.
Right. And they also discuss the false discovery rate, or FDR, which controls the proportion of false discoveries among the rejected hypotheses.
So it's a less conservative approach that allows for more discoveries while still maintaining some control over the error rate.
They explain the Benjamin-Hochberg procedure, which is a widely used method for controlling the FDR.
It's a clever way to balance the desire for discoveries with the need to avoid too many false positives.
Then they move on to techniques for estimating the null distribution, which is crucial for hypothesis testing.
The null distribution represents what we would expect to see if there were no real effect, right?
Exactly. They explain permutation tests, where we shuffle the data labels to create datasets that represent the null hypothesis.
It's like playing a game of chance with the data to see what kinds of results we might get by pure luck.
And they discuss bootstrap resampling, where we create multiple datasets by sampling with replacement from the original data.
This allows us to estimate the variability of our results and construct confidence intervals.
Right. Then they connect these statistical testing concepts to specific data mining tasks, like association analysis and anomaly detection.
So we see how these statistical tools can be used to validate the patterns and anomalies we discover, ensuring they're not just flukes.
Exactly. They discuss how to apply hypothesis testing to evaluate the significance of association rules, using techniques like permutation tests and swap randomization to generate null distributions.
And they introduce the chi-square test as a way to test the independence of items in a contingency table.
They also highlight the challenges of evaluating anomaly detection methods when dealing with imbalanced datasets where anomalies are rare.
Right. Traditional metrics like accuracy can be misleading in those cases.
They emphasize the importance of using metrics like precision, recall, and F1 score, which provide a more balanced view, considering both true positives and false positives.
And of course, ROC curves and precision recall curves are valuable tools for visualizing the performance of these methods across different thresholds.
Well, that concludes our journey through Introduction to Data Mining. It's been a deep dive into the world of extracting knowledge and insights from data.
It has. We've covered a wide range of techniques from classification and association analysis to clustering and anomaly detection, all while emphasizing the importance of statistical rigor and avoiding false discoveries.
Data mining is a powerful field with endless possibilities. As we continue to generate more and more data, the need for effective data mining tools and techniques will only grow.
And for those of you who want to continue exploring this fascinating world, we've included links to the book and other resources in the show notes.
We encourage you to keep learning, experimenting, and asking questions.
And above all, never stop being curious about the stories hidden within data.
Thank you for joining us on this data mining adventure.
It's been a pleasure. We'll see you next time for another deep dive.